Okay, good morning, everyone. Today we'll get into one of my favorite topics, AC analysis or sinusoidal analysis, chapter 5. Note about this is that there is no new analysis technique. Okay, this this is something I think also mentioned repeatedly in chapter 2, but an AC analysis or sinusoidal analysis is mostly about math. Okay, and this math is not, I mean, some people, of course, do hear the word math and become apprehensive, but again, it's not that challenging. The only thing about this is that we use complex numbers. We actually use complex numbers to make the math less complex. And so we'll see, we'll see how we do that. Let's go into the class notebook. All right, sinusoidal analysis. What we look in here is we'll study how AC circuits work compared to DC. When we say AC circuits, the components are still the same. These are the only three components we study: resistors, inductors, and capacitors, R, L, and C. The thing that makes this an AC circuit is the application of the AC source, meaning instead of a DC voltage or DC current, we are now applying a AC voltage or AC current. Okay, so we'll see what roles do these components have to play and how we can mathematically model the relationships between the voltage and current for all these quantities. Okay, so before we get into that, let me go to the beginning in chapter 1 and look at the slide that I usually do on the first day of class, but I didn't get to do it this time because of the holiday. And that is this one. Anyone ever hear of this, the War of Current or the Current War? There was a movie that came about on the series of events a few years ago. I want to say Nicholas Hoult and Benedict Cumberbatch. It's been a while, but I think those two were the main protagonists. Basically, this is a technology. I mean, this is a war of competing technologies. One side you had Edison, the other side you had Tesla. Everybody's heard of both names. Edison was an American businessman, inventor / many different things. Tesla was a mathematician and physicist, researcher from Europe. Edison, this is around the time of late 1800s. Okay, Edison at the time was well established. He had his factory. He had an army of engineers and researchers working for him. And typically, as the case, if you have a corporation, anything that an engineer or researcher or your employee comes up with belongs to that corporation. So there are many inventions attributed to Edison that came out of his business enterprise. Tesla at the time was a researcher working in Europe. He was doing a lot of research in, inductors, coils. Many of the technologies that he worked, research, and published are still in existence today. Many of them are part of our everyday lives. Okay, the electric motor, Tesla coil, mutual inductance, wireless charging, all of those can be attributed to the work that was primarily done by Tesla. That is not to say he was the only one to do this. There were hundreds of researchers who came before him who did a lot of the work, but then he did, and he published, he showed working prototypes of devices and ended up becoming famous for that. Okay, so this is the late 1800s. Edison had his company, was known as Edison Electric. For several years, mergers and acquisitions came to be known as General Electric, GE. Edison Electric is like the precursor. So predecessor, not precursor, predecessor. So Edison Electric at that time was working in DC, right? DC, which is basically direct current, meaning the voltage or current has a constant relationship with time, doesn't change. And then Tesla at the time was in Europe. He was recruited by one of Edison's managers, came over to America to work for Edison in one of his companies. And at the time, Edison had kind of like an unsolvable problem that he put a bounty of $100,000 on it. Like if anybody could solve that, he would pay that person $100,000. Edison was, by all accounts, a mathematical genius. And he was able to visualize problems in his head, visualize solutions in his head, and work through theoretical analysis of a problem. And so he was able to solve that problem. And when he went up to Edison to ask for his prize, Edison supposedly laughed in his face and said that, hey, I was just joking. You're my employee. I'm not going to give you any prize money. This is part of your job duties. By all accounts, Edison was a jerk, first-rate jerk, as most business people are. Well, not tarnish everyone with the word, but if you want to get ahead in this world and if you're running your own business, you have to take hard decisions. And so you come across as jerks. None of us were alive at the time, so we don't know. This is all based on historical anecdotes and narratives, but most narratives just portray Edison as being, as being not a pleasant person to be around. He was a charmer. He could win us, like, if you're a businessman, you need people to give you money. And so he was very good at that. He was successful at running his business. Tesla, not so much. He also had the backing of a lot of people. He got the money, but he not squandered, but he invested the same money himself into new technologies. And then eventually the money ran out. Anyway, so they had a falling out shortly thereafter. And Tesla left Edison's employment and then, worked. They had disagreements between AC and DC technology. So Tesla was pushing for AC. AC is basically voltage or current that fluctuates with respect to time, right? Goes through a positive, negative peaks. DC is constant with respect to time. So from that point on, again, for business perspective and for personal retribution, Edison did all in his power to denigrate Tesla and his work. He would pay anonymous people to put up street shows where they would electrocute animals using AC sources. And so what they would do is they would capture stray animals and they would take AC voltages and AC currents and then electrocute them and show that AC is very dangerous, whereas DC is safe. He would show off his light bulbs or other electric technology and show that DC was safer than AC. The thing that he wouldn't disclose was that AC would be running at hundreds and thousands of volts, whereas his own DC would be running at a lower voltage. And so, just trying to win that competing war. Anyway, late 1800s, there was the World's Fair in Chicago. They all bid on this. Tesla had the backing of Westinghouse, George Westinghouse. Westinghouse, if you didn't know, is still a brand that is in existence today. And they bid about $400,000 to electrify the entire fair. That bid was about $100,000 cheaper. This is about almost a century and a half ago, right? 1880s or 1890s. So not quite 150 years, but at least 125 years. So $100,000 is a lot of money. So they won the bid. They electrified the entire fair using AC technology successfully without any notable incidents. And then, the rest, as they say, is history. The world's first power station, or one of the first power stations, was established near Niagara Falls. They chose a nice even number for the voltage generation based on the AC technology. DC was still being pushed by Edison, but Edison's own engineers and salespeople had a tough time trying to sell DC technologies because it was more expensive. It required more upkeep, and they were losing the bidding wars in every businesses they reached out to. And so after a short time, Edison also had to pivot to AC generation and distribution. And so that's the history of AC versus DC in a very short, brief talk. Again, this is all based on historical anecdotes, but most of it, I would have to assume it's true because there's always, some truth behind, several stories. Yeah. So AC, the question being asked is how and why it's easier to generate. So AC is basically generated by a inductive coil rotating inside a magnetic field. That magnetic field, of course, is a north pole and a south pole. And the rotation can be done as a mechanical rotation that can be done using hydropower, water, or you have wind turbines. So the mechanical rotation moves that inductive coil inside this magnetic field. That magnetic field, again, the magnetic poles, north pole and south pole, result in the electrons moving back and forth. So you have positive, negative, positive, negative. So circular rotation between a magnetic north and south pole results in a sinusoidal varying waveform that goes, up, down, in a sinusoidal shape. And so when we say it's easy, it's easier than DC. But the funny thing is, everything that we use in everyday life runs on DC. Every single thing that we use runs on DC. The monitor, the projector, the television, your smartphones, tablets, everything runs on DC. That's why you plug in an adapter into the wall every single time you want to use a device, is because that adapter converts the AC into DC. AC is also easier to transmit. So based again on the principle of transformers, you can easily step up, meaning increase the voltage to hundreds of thousands of volts and transmit it over long distances. When you transmit over long distances, so again, voltage is increased and you transmit over long distances. And this is, again, this distance is hundreds of miles long, right? What happens over hundreds of miles? Resistance is rho L over A. So the longer the length, the higher the resistance. So even if the resistance is very small, the length is hundreds of miles, that cumulative effect of that length results in power losses. Power loss is I squared times R. P is V times I in terms of resistance is I squared times R. Meaning the higher the resistance and higher the current, the more your loss in that power transmission. The goal is to keep that power transmission low. So if you wish to increase the power being transmitted, you either increase the voltage or you increase the current. But if the choice is between voltage or current, then voltage is the better choice. And so that's the reason why the rest of the world, or most of the world, uses a different voltage than North America. Which brings me to that question that I stated on the first day of class. General knowledge question. What is the voltage rating of the power outlet? 110, 120 volts. That is because at the beginning, when they set up the power station, people are apprehensive, right? It's electricity. It's something that nobody has ever seen. The only brush with electricity people have is if somebody's struck by lightning, right? So, and that's dangerous. So when you set up these bare wires that are carrying electricity through it, people, again, and for good reason, because people did get electrocuted. There were lots of incidents when it first set up. So whether it was DC or AC, people were electrocuted. People did die as a result of this new technology. So people were apprehensive. So instead of choosing like a higher number, they chose a nice round safe number of 100. And they built a 10% tolerance in it. So it became 110. And then once the infrastructure is set up, you can't like change the entire infrastructure. So, it's between 110 to 120 volts. The rest of the world followed shortly thereafter. So instead of sticking with 100 volts, they stepped it up to like 220 or 240 volts. It's about 220 to 240. Yeah, that's the reason. So you can give more power without increasing the current. So if you've ever, so power in residential streets, there are some light poles around campus. And of course, if you go down a residential street, you can see electricity poles going down a street. And sometimes you might see a metallic cylinder around a wooden pole. That cylinder is a transformer, not quite Optimus Prime, but what it will do is it will take the voltage coming in and distribute into multiple different homes. If you ever heard or read or witnessed a hot tub being installed, you would have ever heard that to install a hot tub, you need a licensed electrician to come out and do something? Anyone ever hear of that? Right? What they're doing is they're taking two phases of 120 volts and combining them together. So you have, this is 120 volts, and this is 120 volts. What do you get if you combine them together? 240, right? 240 volts. And so what that electrician is doing is laying down electric lines to taking two separate lines, two separate phases, and combining them together, because a hot tub requires a whole lot of power. Nothing else in a residential environment requires that amount of power. Not your washing machines, dryers, ovens, nothing. hot tub does require a huge amount of power. So that's what they're doing. Anyway, so that is kind of like a brief introduction. If you have the time, you can check out this movie. This came out in 2017 or 2018, I believe, known as War of Current. And well, that's what it is. So coming back to chapter 5. These are some representative examples of AC waveforms. We are not going to study all of them. The only ones we're going to study is basically the one at the top. So again, you don't have to draw or write any of these down. These are just for informational purposes. Basically, a DC waveform, when plotted with respect to time, and now you will see waveforms always plotted with respect to time, right? We're talking about AC voltage or current. Basically, values fluctuate with respect to time. So time is always on the x-axis, always. And the y-axis is where time t equals 0. And this quantity could be voltage or current or power, VI or P, VIP, okay? So depending on the shape, if the value remains constant with respect to time, it is flat, it is a DC waveform. When I say waveform, it simply means voltage or current or power. It's just describing the graphically, that's all. So when I say waveform or signal or function, they're all synonyms of each other, okay? So a DC waveform is essentially a flat line, right? The value does not change with respect to time. Any other waveform is AC. Could be anything. If it has a particular shape, we can refer to it as triangular, square, rectangular pulse, ramp. Square and rectangular are exactly the same thing. Square is kind of, it's not even kind of like a term that I might agree with, because square would require that the x and the y values be the same, right? But x is time and y is the quantity. So you can't exactly make it same. If you view it differently, like if you zoom in one axis differently than the other one, you can get a square waveform out of any rectangular waveform, right? But the primary waveform that we are concerned with for this entire chapter is this, sinusoidal. Yes. That's one way of generating it, yes. The question being asked is if we can use DC to generate square wave, meaning you just turn it on and off, and that is absolutely correct. Yes, you can. If there's fast switching, you just turn it on and off, and it becomes a square waveform or a rectangular pulse. So what was I saying? Oh, sinusoidal waveform. So the primary or the only waveform that we are concerned with is the one at the top, which is known as sinusoidal. Mathematically, it's simply represented as sin x or cos x. Okay, that's the mathematical representation. And we will look at each quantity in detail in the next few slides. This is what the entire chapter is, mathematical representation. Okay. So this is a standard expression. V of t is represented by Vm cos omega t plus theta. Instead of V, I would use the term X. X of t is Xm cos of omega t plus or minus theta, where X could be voltage, could be current, could be power. Okay. So this could represent either voltage or current or power. Applies equally to all. So sinusoidal waveform that goes to a positive peak and a negative peak, coming back to 0, can be represented mathematically using this equation. The M stands for magnitude or amplitude or peak. So this Vm is also represented as Vp. And this is very important for you to understand. If you are in the lab, if you are using an instrument, or if you perhaps talk to any of your peers in a different class that use a different book, they would be referring to VP. It's the exact same thing as VM. What it is representing is the value of that quantity on the y-axis. Remember, the quantity value is always on the y-axis. X-axis is always time. The quantity value is always on the y-axis. And then, of course, this could be IM or IP. It's the y-axis values. Okay. And then we have omega, angular frequency, lowercase Greek letter omega, angular frequency in radians per second. And then theta, the phase angle, again, Greek letter theta, phase angle in degrees. There is a specific reason why we keep the phase angle in degrees or the phase in degrees and not combine it in radians. Okay, and you'll see that. It's because of mathematical representation. We will use that. Omega, in terms of frequency, is 2 pi f. We will look at all three of these quantities, Vm, omega, and theta, individually on the next 3 slides. Okay, so don't worry about, hold off your questions until we get through those 3 slides. Okay, so Vm is magnitude or amplitude or peak, y-axis values. Omega is angular frequency, 2 pi f on the x-axis, t, and then theta is the phase angle in degrees. Each quantity has an individual unit. As an individual quantity, it has individual units, but this entire function is describing the voltage as a function of time. So when you write this expression, the overarching unit for the entire expression is always that quantity. In this case, it's volts. If it's I of t, it would be amps. If it's P of t, it would be watts. Any questions? Okay. Individually, the 3 quantities have different units, but overarching is basically what that quantity is. V of t, volts. And then this is another expression that you should be familiar with. Again, mathematical expression is something that you all, I would assume that all of you would probably know this. Sin x is cos of x minus 90. All right, let's look at what, yes. Yes. All right, okay. So for a sine wave, the magnitude means it's the amplitude, or it also means the peak value. It only describes one peak, not both. It's only describing one peak, okay? But you can apply it to both. You would assume that because it's a sinusoidal waveform, it's symmetrical. And if it's symmetrical, then it's also describing the negative peak, negative value. So let's look at waveform 1, 2, and 3. Waveform 1 has a peak value or magnitude of 0.5. Waveform 2, it's 1. And waveform 3, it's 2. It's noted by this first quantity right here. Second one is simply sine theta, meaning it's just 1. Okay. So again, Vm or Vp is describing one peak. If you wish to describe that waveform in its entirety, you would use a term name P dash P, just 2 times Vp or 2 times Vm. P dash P stands for peak to peak. both peaks. Okay. So again, peak values describe the value of the quantity on the y-axis. Then come to frequency. If you look at any sinusoidal waveform, it starts at 0, goes to a positive peak, comes back to 0. We call this as the positive half cycle. And then it goes negative and then comes back to 0. And we call this as the negative half cycle. The moment where the waveform goes from 0, goes to positive, negative, and then comes back to 0, we say it has completed one full cycle. Okay, one full cycle. So 2 half cycles added together would give you one full cycle. That full cycle is mathematically represented by the uppercase T. X-axis is always time. Typically, the units are always seconds. And so T is known as the time period of the waveform in seconds. Okay, so it goes up, goes down, goes up, goes down. The number of cycles that a waveform completes in 1 second is described as the frequency of that waveform. So frequency as the name suggests, how frequent the waveform is. Frequency is lowercase f. It's equal to number of cycles in 1 second. The relationship between f and t is that they are inverse of each other. And also, as we saw in the previous slide, omega, the angular velocity or angular frequency, is 2 pi f. 2 pi, again, is a full circle. It goes back to the basics, right? We generate inside a rotating magnetic, inside a magnetic field. So 1 circle gives you 1 cycle. So omega is 2 pi f. F is 1 over t. T is basically the number of cycles in the length of that 1 cycle in seconds. Okay. Frequency is the number of cycles in 1 second. So again, general knowledge question: what is the frequency of the power outlet? Anyone? Of our standard power outlets, North American power outlets. 60 hertz. It's listed there on every single adapter, every single appliance that you've ever used. So that's why I said general knowledge question. And I mentioned this, I think, on the first day of class too. Outside of North America, it's 50 hertz. So if it's like 220 volts, 240 volts, then it's 50 hertz. I actually don't know the history behind why that is, but it's 50 hertz. So most adapters that we use nowadays will have rating which says you can use it. It will say input 100-240 volts and 50-60 hertz, meaning you can safely plug that device into any power outlet anywhere in the world. You don't need to do an electric conversion. You might need to do a physical conversion because, again, physical prongs are different throughout the world, but electrical conversion is no longer needed. But again, just to be safe, you should look at the adapters that you are using. So the adapters would state input and output both. So 60 hertz means it goes to 60 cycles in 1 second, meaning it goes up, goes down, goes up, goes down 60 times in 1 second. Now, if you're Dr. Strange and you could slow down time, stick your finger in the wall, you could feel it going up and down to zero, down to zero, up, down to zero. Thankfully, none of you are Dr. Strange, so don't stick your finger in the wall. Anyone ever get zapped or electrocuted? You feel a zing, not a pleasant sensation. Depending on the voltage, it could be fatal. But the reason for the zing is because the voltage, as fast as it's moving, it goes to a maximum value and then goes down to zero. And so it kind of like throws you off. If it's DC, and I've only read this, thankfully I've never had the experience of being in touch with a high voltage DC wire. You get stuck. That's what I've heard. And then that's it. Yes. What voltage? Actually, that's a good question. What voltage would you get stuck? I don't know. I'm assuming 100 volts. 100 volts would also be enough. I mean, people get electrocuted even with 120 volts AC, because if you just get stuck, your body is getting that energy that's coming from the power outlet. It's just that if you're inadvertently in contact with a regular normal power socket, then because if it's an AC voltage, you get the zing feel and you're like jump off, but you could still get burns on your skin. So it depends on how you get electrocuted, and every person's body is different, right? The water content is different. Everything is different. So in general, I wouldn't say it's safe, but in general, I would say like just a minor accidental glance would not be fatal. I want to say in general, it would not be fatal. Yeah. Yes. So that's a good question. So how are the power outlets connected in our residences and everywhere else? They are all in parallel. If it's in series, then you would actually they wouldn't work without something being plugged in there. If it's in series, meaning series connection, everything needs to have a closed pathway. Series connection wouldn't work unless something is connected. So everything is in parallel. So it's all cumulative effect. So the question being asked is, how does it affect the amperage or the wattage? That goes back to the point I made earlier. Nothing in a residential household is of high enough energy consumption. The most energy consumption would come from your HVAC unit, because that runs constantly, right? That's the only appliance that runs constantly. Everything else is like occasional. If you have a electric or a gas stove, like cooking, you're not going to be cooking 24 hours a day. It's not turned on 24 hours a day. That's another big consumer, right? Then washers, dryers, those are again, maybe weekly, maybe every few days, but not constantly. And even when it's run, it's only for a few hours, not even one. It's one cycle, maybe 40, 45 minutes. Not much power consumption. So just by itself, an appliance could be like a high consumer, but overall across time, like across a period of 24 hours, that is not much. And so maybe if you had like multiple washing machines in there, like, if you're running like a laundromat or something, and then you had like multiple cooking ranges in one area, then you probably overload the circuit. But other than that, it wouldn't be a problem. It's all basically divided in parallel. Yeah. All right. Good questions. One more point about 60 hertz. You might think that it's very high, right? We say 60 hertz in 1 second. That's a lot. That's a lot of cycles in 1 second. But in reality, that is actually a very, very, very low frequency. 60 hertz is something that people like me probably can't even hear anymore. Okay. Normal human range is stated to be as 20 hertz to 20 kilohertz. What? 60 hertz is very low frequency. If you want to reproduce that kind of sound, you need like a huge, big subwoofer to even produce something below like 100 hertz. The reason for the physical size is the wavelength. Wavelength is inverse of the frequency. And so the lower the frequency, the bigger the speaker that you need to reproduce. Anyway, coming back to the point I was making, real life frequencies are much, much higher. Normal human hearing range is, of course, up to kilohertz, like thousands of kilohertz, 15, 16,000 kilohertz. The frequencies that we use for electronic or electronic transmission is much higher. AM and FM radio, the call sign or the name of the station has a technical meaning behind it. 680 AM stands for 680 kilohertz. That is the transmission broadcasting frequency of that radio station. 101.7 FM is 101.7 megahertz, 10 raised to 6. So AM is broadcast in the 600 kilohertz range. FM is broadcast over 100 megahertz. Wireless phones, microwaves, your wireless routers, they all run 2.4 gigahertz or 5 gigahertz bands. That's 5 into 10 raised to 9. Yes. Sorry, what? It's not about clearer sound. It's just, it's actually two different things. AM is amplitude modulation, meaning you're modifying the amplitude, the y-axis. FM stands for frequency modulation, meaning you're modifying the x-axis. There's two different technologies. So there's a lot more that goes into that. The thing is, lower the frequency, the farther it can travel. So AM is a lower frequency, it can travel a lot farther than FM. That's one thing. And then, of course, sound clearer and everything. That's, again, that goes into like communications. If you're interested, you can take EE 314. It's communication systems. It's for EE majors. But if it works in a tech elective, you can take that class. Yes. I see what you're saying. Yes. So I think the question being asked is about before we had Bluetooth, you had these adapters. So they were FM transmitters. You could take the output, the headphone output of any device you had, you plug it into this FM transmitter, and that FM transmitter would become a mini radio station inside your car. And so it would broadcast that signal out at a particular frequency, like an FM radio frequency, and then you would tune or you would match the frequency of your radio receiver to the transmitting frequency. And so the sound from your device, let's say it was like a portable Walkman or Discman, portable audio device, would now be broadcast inside your car. Anybody could listen to it if they knew that frequency. But yes, that's what it is. Okay, good talk. Let's see. Phase is the last quantity. Remember, I said we keep the phase separate as degrees. The reason for that is it describes the moment in time when it crosses the x-axis. Okay, so this is t equal to 0. The value of these waveforms is all 1. It's not 0.5. And this on the x-axis is t, time. If you look at the waveform 1, 2, and 3, if you look at waveform 2, it crosses the x-axis when time t equals 0. Hence, the phase for that waveform is said to be 0. I'll see that. Waveform number 2 crosses the x-axis at time t equal to 0. Now, t equals 0. These are positive numbers. These are negative numbers. +1, +2, +3 on the right, -1, -2, -3 on the left. But mathematical representation, what does it actually mean? It's referring to time. Plus numbers mean the time is yet to come, means it's the future. Minus means it's already gone by, it's the past. So take 10 seconds and think about it. Does that make sense? Right? Positive numbers on the time axis means it's the future. Negative numbers means it's the past. So if you look at waveform number 3, the one in blue, waveform number 3 has already crossed the x-axis, -1 or -2 as the case may be. Let's just say it's -1, for instance. Right? It's already crossed the x-axis. So the moment in time when the waveform in blue crossed t equals 0, the waveform in black, which is waveform number 2, was yet to come. So the waveform in blue, waveform number 3, is ahead of waveform number 2. And that is indicated by the positive phase number. Okay. It can also be described as the distance from time t equal to 0. So mathematically, that number, this distance from time t equal to 0, can be described as the phase. Okay. It's already ahead in time, so it's represented as a positive phase number. Yes. On the x-axis. On the x-axis. X-axis is time, so it's describing this distance right there. It's the moment in time when it crosses the x-axis. So when does it cross the x-axis? And so that, yeah, that's the, so it crosses the x-axis here. And so that's why we say, and it's in the past, I mean, it's already gone by. It's, we missed the bus. It's already gone by. So the bus is ahead of us. So in that sense. And in the same vein, waveform number 1, waveform number 1 is behind because it has yet to cross the x-axis. It will arrive later, right? It will arrive later. And so the phase relationship for that is indicated by a negative sign. And the reason, so don't get too bogged down into this explanation. Just think of it in terms of mathematical terms, positive phase and negative phase. If the waveform is ahead, we say it is leading or leads. If the waveform is behind, we say it's lags. Okay. And it'll be a mathematical representation. How much time do I have left? 7 minutes. Okay. And again, as I said, there's a reason we keep it separate, because we'll describe it as a vector. And for a vector, we'll need that phase angle. So before I go to the next one, let me ask you, we saw those waveforms, right? All of them are symmetrical about the x-axis, half above, half below. What is the average value of that waveform? 0, right? 0. But energy is still being transferred. So how do we mathematically represent that? And think of it in this term. If all peaks were positive, right? All peaks were positive. You had positive, negative, but you flip the negative peaks to go above the waveform. Now you have all positive peaks. You think of these as mountains of dirt and you flatten them out. You get a value that is equal to that DC value that would generate the same energy or deliver that same energy. Does that make sense? Right? So they had a problem at the beginning, meaning how can we mathematically describe this? Because if you take the average, it's just 0. So they decided instead of taking the average of the waveform, we'll first square the waveform and then we'll take the average. And because we squared the waveform at the beginning, at the end, we will now do a square root. So they came up with a new term called root mean square. It literally is the square root of the average of the square of the waveform. Average is, of course, another term for, mean, of course, is another term for average. So again, this describes the average DC value of that waveform. And it's simply, or popularly known by its acronym called RMS. It literally is the square root of the mean of the square of the waveform. So if you look at the mathematical equation here, we have V of t We first square V of t, right? That's the square. That's the initial step. Then we sum it up. Integrating is nothing but summation of all the individual slices, dt, right? Individual slices. So 0 to t, one time period, you add up all the slices, integrate from 0 to t. Then you take the average, which is 1 over t. And because we took the square initially, we now take the square root, which is right here. And so again, literally is nothing but the square root of the mean of the square of the waveform. It applies to both voltage and current. Now, we're talking about average, right? Because we want to calculate the average power in a resistor. Remember, I said we use the exact same equations. For a resistor, power can be given as V squared divided by R, or I squared times R. So if it's talking about DC, we simply use those equations. We talk about AC, we can still use the same equations, except we have to put the right numbers or the right values in there. So we plug in the RMS value of those quantities. And so the average power delivered to a resistor would be V RMS square over R, or I RMS square times R. That's all it is. There is a mathematical derivation behind this. And so for sinusoids and sinusoids only, if you plug in V of t or I of t as sine x or cos x, you can solve this, and the relationship you obtain is VRMS is Vm, the peak value, divided by root 2. Okay, or you can write Vm is root 2 times VRMS. Remember the sketch I just drew. You have mountains of dirt and you're flattening it out. The peak of that mountain will always be higher than the flat line. So the peak value, Vm, will always be larger than the VRMS value. Or the current, doesn't really matter, right? The peak or the magnitude of that waveform will always be higher than the RMS value. Okay, and this is true only for sinusoidal waveforms. There is a derivation. I usually don't do the derivation for non-E major classes. So if a student is interested, you can come by my office. I can show it to you. But again, only thing you need to understand and retain is that the RMS value is the peak value divided by root 2. What is what is the voltage that comes out of our power outlet? RMS value describes only one value because it is only one value. Peak just describes one instant in time, but it doesn't describe all values. Power outlet, we say 120 volts. Yeah, it's RMS. All meters, all measurements are always done in RMS. Unless it explicitly states its peak, it's always RMS. So 120 volts, RMS. Got about a minute left. Let me introduce this quickly and then we'll. So sinusoidal voltages are easier to generate. They're easy to handle mathematically. Derivatives and integrals of sinusoids are also sinusoids. Sine x is cos x is sine x, makes it easier. Differential equations have to be solved, but we don't do that because we are going to use complex numbers to represent our sources and our components. So when we use complex number math, our differential equations are reduced to simple circuit analysis problems. Okay, simple circuit analysis problems. Sources are not replaced, but represented mathematically as phasors. Resistors remain the same. Inductors and capacitors are energy storage devices. If it's AC, energy flows in, it flows out, flows in, flows out constantly. Exchange of energy takes place. And so we model those using complex impedances. And we'll see that in next class. I'll be in my office later this afternoon for office hours if students want to come and have Any questions? But we'll pick up here again on Friday. Get started on the homework. I'm going to take a look at the homework and see if there are any topics that I've not yet covered for today's class. If that's the case, then I will extend it until Friday, but get started on that AC analysis homework. Okay, most of it is concept-based short answer questions.